In this lecture today, we are going to learn about oxidation, reduction reaction. So here we will try to understand what do we understand by oxidation and what do we understand by reduction in the upcoming slides. So let's get started. So in order to understand that, first we will have a look into electron transfer reactions. So if you have done types of chemical reactions, there are a few different types of chemical reactions, and electron transfer reaction is one of them. Okay, where the electrons are transferred, and that is how the reaction proceeds. So if you have a look over here, there is a nice shiny copper wire which is placed in this beaker that is containing AgNO3 solution, that is silver nitrate. Okay, so let's say some time is spent, it has been there for a while, let's say 15 minutes, 20 minutes. So what will happen? You will start seeing this thing. Okay, over the time what will happen, the copper atoms in the wire, they will be displaced into the solution, and the silver atom from the solution will be depositing here on the wire. Okay, so what's going on here, the solution turns blue because copper 2 ions are released and they're blue in color. That's why you see this nice beautiful blue color. So essentially this reaction is happening. We will study in details what is this reaction about. So copper, first of all, it was in the solid form. It went into the AgNO3 solution, and then what happened, the silver got deposited, and then we had copper nitrate in the solution form, in the aqueous form. Okay, so now let's try to break down this equation in the ionic form. Okay, because we know that when anything is in the aqueous state, for example AgNO3, it can be dissociated. So copper nitrate produced is completely dissociated into ions in the solution like this. We will see that. So let's go ahead and have a look on that thing. So here's our equation in the ionic form. So this is called ionic equation. So solid, it will stay as it is. You can't break down into ions. For here, AgNO3, it will dissociate in the solution, so you can write Ag plus and then NO3 minus. So again your solid will remain intact, and then copper nitrate, it will be dissociated, so you can write like this, right? And then similarly for NO3. So this form of equation, what do we call them as? Total ionic equation. It contains all the ions that are present in the solution, the total information. Okay, and then it is in the ionic form. So it's a good idea to call it total ionic equation. So now if you notice one thing over here, that is if you pay attention on the NO3 ions, what happens? They went in as 2NO3 minus, and they're coming out as same. No changes happening over here. However, if you observe copper, it is becoming copper 2 plus, right? Before it was like this, after it is like this. Now this is Ag plus. Now before it was like this, now it is Ag solid. So they are undergoing some change. But if you look at this is not undergoing any change. It came out as it is. So these are called spectator ions. So they are just watching there. They're not participating. They are just there. Okay. So they don't actually, they are not contributing to the reaction, so you can cancel them because they have same quantity on both sides. So when you get rid of them, you get this nice equation. We call it as net ionic equation. Okay, so when you get rid of any spectator ions, so you're left with copper solid and 2 Ag ions, and then you're left with 2 Ag solid and copper 2 plus ions. So you cancel these. So this form of equation is referred to as net ionic equation. Okay. Now let's move ahead. Since we have a good idea about what is net ionic equation, what is total ionic equation, on the exam you might be given some reaction, and then the teacher might ask you, can you write the total ionic equation, or can you write the net ionic equation? Then you should be able to do so, and then we will practice a few questions about it. In this slide, we are concentrating on the atoms those are left. So we are left here with copper solid. Let's see, it came in as copper solid. It came out as CO2 plus. So what happened during this process? So it lost 2 electrons, right? How copper can become copper 2 plus? By losing 2 electrons, right? So loss of electrons in chemistry is referred to as oxidation. Okay, so the loss of electrons is called oxidation. So we can say that copper is undergoing oxidation. Now let's focus on Ag plus. So if you focus here, it was Ag plus, now it became Ag. What is happening here? When you go from the plus state towards the neutral atomic state, that means you might have gained electron. So the gain of electron is happening in this part. In chemistry, we say that it is the process of reduction. Okay, so if you're gonna read here, gain of electrons is called reduction. Okay, so that means oxidation is also happening and reduction is also happening. So what do we call this type of reaction? We call it as oxidation reduction reaction, because both are happening over here. Okay, so we say oxidation reduction reaction. This reaction is redox reaction in short. So Red for reduction and then ox for oxidation. So redox, every time we can't write this big name, so we choose a simple name, redox reaction. Okay, so I hope that makes sense. Now moving on, we have these little definitions for a quick review. What we just did, the process in which one or more electrons are lost by chemical entity, we call that as oxidation. Similarly, the process in which one or more electrons are gained, we call that as reduction. And then again, which is oxidation reduction reaction, the reaction in which one or more electrons are transferred, right? So one is losing electron and the other one is gaining electron. Okay, so that is your redox reaction. Now let's move ahead. As we know about oxidation reduction, now we understand about that. Let's try to concentrate on half reaction equation. So what do we understand by that? A half reaction equation is a chemical equation, is a chemical reaction equation that represent one of the redox reaction part. So what do we mean by that? So the half reaction will either just show you reduction, or it will just show you oxidation. So for example, if you pay attention on this reaction equation, copper solid turning to copper 2 plus 2 electrons. So what is happening during this journey? It is losing 2 electrons. This is what is happening, loss of 2 electrons. So what is this? This is called oxidation half reaction. Okay, what do we call it as? Oxidation half reaction, or half reaction for oxidation, right? Now similarly, it can be for reduction also. We can give you a reduction reaction only. Okay, then you will call that it is reduction half reaction. So for example, in this slide, what is happening to Ag during this journey? It is gaining electron and becoming Ag0. So this reaction is called reduction half reaction. What do we call it as? Reduction half reaction. Okay, I hope that makes sense. Now they're saying if we compare the number of electrons in the two half reactions, okay, they're not the same, right? So in copper, uh, from going from solid, and then it was losing 2 electrons. Okay, so there is a loss of 2 electrons, but if you pay attention on this one, which is Ag, so Ag is plus 1, so it needs to have 1 electron to become Ag. So here it is gaining 1 electron, here it is gaining losing 2 electron, right? So the number of electrons lost in a redox reaction. So I'm talking about redox reaction now. Okay, when you want to combine them, when you want to add oxidation half reaction and reduction half reaction, you are adding them, this plus this, to form a full redox reaction. Okay, which is this one. So what will happen over here? You can't add unequal electrons, so you have to make them same. So how this can be turned to 2? You multiply this full equation by 2. So what would be the result? I'm going to write that when you multiply by 2, it will be 2Ag plus 2 electrons becomes 2Ag, right? Now you can go ahead and add them. Okay, so this is one of the rule. So when you will add them, you will have copper plus 2 Ag ions, which is over here, and then on that right hand side of the arrow, you have copper 2 plus and then 2 Ag solid, right? So this is your redox reaction which you got by adding the two half reactions. So this is oxidation half reaction, and this is reduction half reaction. Okay, so very simple, very easy. So let's move ahead. So we are going to discuss about this question as we were discussing previously as well. So what we have is this question over here: aluminium S plus 3 Ag ion, aluminium 3 plus and 3 Ag solid. So aluminium is turning to aluminium 3 plus. This is undergoing loss of electrons. So this is your oxidation half reaction. So half reactions essentially they deal with the one part, either oxidation or reduction. So oxidation half reaction would be aluminium turning to aluminium 3 plus plus 3 electrons, right? So this is one part of your answer. And then Ag, if you concentrate over here, 3 Ag ions, they are turning to 3 Ag. This is your reduction half reaction, right? So it should gain 3 electrons to become this, right? So this is your reduction half reaction. Okay. So this is the method how to do that in steps, in order to guide you through the process. These simple steps are written over here, and then these are the answers for this question. So moving ahead, I hope this makes sense for you. We have few more practice problems. Let's try to have a look on those. So these are the set of practice problems which you see right over here for additional practice. So you have to write oxidation and reduction half reaction equations for the following reactions. So you can do them, and then we can discuss the solutions if you struggle with these. And there are a few more questions. Identify the reactant oxidized and reactant of reduced, right? So because we did one question, so just to give you an idea, so let's say Ag plus, sorry, not 3 plus, just plus. Let me rewrite it. Aluminium plus Ag plus, it's turning to, let's say, aluminium 3 plus. Okay, in some part. So this reaction, if you notice over here, aluminium turning to aluminium 3 plus, this is undergoing oxidation. So this is the reactant that is oxidized, right? and the reactant that is reduced is this one, right? So this very simple, we can do it. You just have to see who's losing electron and who's gaining electrons, and then write the oxidation and reduction half reaction, again similar question, and then you have to see and work on these questions. Okay, so the next topic we are going to concentrate on is oxidation numbers. Okay, so chemists use a type of electron bookkeeping to keep track of which atoms are losing electrons and which atoms are gaining electrons in a redox reaction. So as per our previous discussions, we saw how, let's say, copper is oxidizing to copper 2 plus, right? So we have to keep a track. This thing becomes important in redox reactions. So in this system, an atom's oxidation number, also known as oxidation state, is defined as apparent net electric charge that the atom would have if electron pairs in covalent bonds belonged entirely to the electronegative atom. So the oxidation number system is a useful way to keep the track of these electrons. Okay, but they do not usually represent the actual charge on atoms. An oxidation number can be positive or can be negative. Let's look into some examples. So for example, let's talk about sodium. It has atomic number 11, and this is its electronic configuration 2, 8 and 1. Okay, so it needs to lose one electron to become stable, right? So it will become 2, 8 if it gets rid of this one electron. So 2, 8, when it gets rid of this one electron, it will have Na plus 1. It will become Na plus 1. So plus 1 is the oxidation number for sodium. Okay, this is how it works. Let's see one more example. Uh, for example, let's talk about lithium. So lithium is atomic number 3. It is 2 and 1. It needs to lose one electron, okay, so that it can become stable, right? It will have two. So lithium has oxidation number 1. Okay, similarly you can try magnesium, calcium. They will have oxidation number 2. Okay, because their electronic configuration is something like this. They have 2 at the end, right? So they need to lose 2 electrons. Now let's talk about the negative oxidation numbers. So negative oxidation numbers, let's talk about chlorine. It's atomic number 70. So it's having this electronic configuration, right? 287. This is how we write it, right? And then it cannot lose 7 electrons. It has two options, either to lose 7 electrons or to gain 1 electron, right? So to gain 1 electron is a better option for him. So what he will do, he will go ahead and gain 1 electron. So chlorine will become -1 because electron is carrying negative charge, and when it will gain that, it will become chlorine -1, and what would be the electronic configuration? 288. So the oxidation number for chlorine is -1. So this is how you can find the oxidation number for different atoms, right? Now moving on, let's go ahead and try a few problems as we move ahead with our discussion for the oxidation numbers. Okay, oxidation number, a number used to keep track of electrons in oxidation reduction reactions according to certain rules, are known as oxidation state. Okay, so these are there are some rules we have to keep in mind before assigning oxidation numbers. What are those rules? Let's go ahead and have a look on them. So you have to apply these rules to assign oxidation number to the atoms or ions for most of compounds, right? So what's the first rule? The sum of the oxidation numbers of all atoms in an electrically neutral compound must equal 0. Okay, this rule is often referred to as zero sum rule. Okay, so let's say if we have NaOH. Okay, so I just told you Na has +1. Okay, so this OH part should have -1 because NaOH is a electrically neutral compound, right? So if this is +1, this should be -1. So the sum of the oxidation numbers for all the atoms in a electrically neutral compound, it is turning out to be 0. Next is the sum of the oxidation numbers of all atoms in ions containing two or more atoms must equal to the overall charge of the ion. Okay, so if you have an ion, okay, then what would you do? For the ion, the sum of the oxidation numbers of all the atoms, whether it's two or more, okay, they must be equal to the overall charge. Okay, what could be one of the example? Let's see if we have in the next slide. Yeah, we have few over here. So for example, let's try to have a look in this one. An atom in an element is zero. Okay, the oxidation number is zero. So for example, you just have sodium, you just have oxygen, just have ozone. So these you will treat as oxidation number 0. And then you have monoatomic ion. Okay, so what does that mean? You just have mono means one. If you have just one ion, for example Na plus, this is present in the reaction, so what is its oxidation number? Plus 1, right? So the charge of ion, this is minus 1, right? Similarly you can do Mg plus 2, so this is the oxidation number would be plus 2. And then fluorine is minus 1 in its compound, so this you have to keep in mind. Fluorine, oxidation number you will have minus 1. Okay, you will always keep it minus 2. Okay, sorry, minus 1. And then for oxygen you will always consider it equal to minus 2. This you have to keep in mind, right? So if you want to find, let's say, the oxidation number for H over here, so you will say, you will always keep in mind oxygen is always minus 2, so this side should be plus 2, right? Because this is a neutral atom, and then this is a neutral molecule. So two hydrogens have plus 2, right? So two hydrogens have plus 2 oxidation number, so one hydrogen will have plus 1. Okay, let me do it again. So what we are saying is that you have to keep always this thing in mind, that fluorine you will treat as oxidation number minus 1 and oxygen as minus 2, right? You can see from the electronic configuration as well, that fluorine will have minus 1 and oxygen will have minus 2. Now for water, let's say, oxygen, you already know it is minus 2 always, and then this hydrogen, two hydrogens are present, so these two hydrogens should collaboratively have plus 2 oxidation number, right? So this is the thing, so two hydrogens are having plus 2 oxidation number, so then one hydrogen will have plus 1 oxidation number, right? So depending upon what type of question you are being asked, and let's say the examiner asks you hydrogen, can you calculate the oxidation number of H in this water molecule, then you will say it's plus 1, right? Hydrogen is plus 1 in its covalent compound, so wherever hydrogen is forming covalent compounds, you will treat it as oxidation number plus 1. For example, H2O, you just saw HCl and H3, and then this is the example, exception, CaH2. Okay, and then moving on, let me clear this up a little bit, and then we move on with our discussion of oxidation numbers and its rule. How do we assign them? The convention is to write actual charges on ions as n plus or n minus, right? So whatever the number is, n stands for the number, it would be plus 1, plus 2, whatever n is, so you have to write that. So for example, assigning oxidation number for a molecular compound, there's a one sample problem. Let's do it together. Assign the oxidation number to all atoms in a molecule of carbon dioxide. Okay, so let's go ahead and try to do that. Carbon dioxide, what is the formula for a molecular formula for this one? It is CO2, right? So CO2, it is an electrically neutral compound. Okay, and then that means whatever numbers we put over here, they should add up to give you 0 charge, right? As per our discussion, we just did that oxygen always carry minus 2, right? So for each atom of oxygen, it is minus 2, right? So this you need to know, but over here CO2 we have 2, so that means overall oxygen is carrying minus 4 over here. This is the oxidation state for this O2. So what should be the charge, or what should be the oxidation number for carbon? it should be plus 4, so that they add up to give you 0, right? So you will say that carbon corresponds to plus 4 oxidation state in this molecule, and then one oxygen molecule, it is corresponding to minus 2. This should be your answer. Does it make sense? I hope it should. And then let me clear it up a little bit, and then we move ahead with our discussion, sample problem solving. Similarly, let's go ahead and try one more problem. We have NO3 minus now. So what would we do in this one, right? So the overall charge of this molecule, of this ion, is -1, right? So all of the oxidation numbers, whatever I put here, they should add up to give me -1 as the answer. Yes. uh, Earlier it was CO2, there was no charge, so they should add up to give 0, but now this thing has a charge, it is iron. Okay, so let's get started with oxygen, because I already know about oxygen. Oxygen, one molecule is -2. I have 3 oxygen molecules, so that means that is -6, so this should be -6. Now what should I add up here so that it gives me -1 as the answer? So I have situation like this. X plus -6 should give me -1. So what should x be equal to? So I will solve it, and then my answer would be +5, right? So you will rearrange your equation and your answer would be +5. So that means nitrogen oxidation number should be +5, because when they will add, they will give overall charge -1 to this molecule, right? So this, all this thing, calculation nicely explained with the text and solved here for you for your convenience. You can go ahead and read that. So in nitrate ion, you will say nitrogen atom is carrying +5, and then oxidation number for each of the oxygen atom is -2. So you have to mention that you're telling it for one oxygen atom, right? So I hope that is making sense so far with the oxidation numbers, and then how do we calculate it in a neutral compound, and then how do we do it in ionic compounds, right? And then again we have a similar kind of problem. Let's go ahead and do that together. So what do we have over here is Na2S2O3. Okay, Na2S2O3. So again, let's start our discussion with oxygen. So one oxygen corresponds to -2. I have 3 oxygens, so 3 oxygens correspond to -6. So I'm done with this one. We just did sodium also, very simple. Sodium, one sodium corresponds to +1, right? When we just started discussing about oxidation numbers, so we just learned that sodium is +1. So it's a good idea, maybe when you will be practicing also, then you will kind of memorize them, right? Or you can just look over the periodic table, try to draw the electronic configuration and see how it can become stable, like I just showed you, right? So I have 2 sodium atoms right over here, and then it would be +2. So this means it is +2, right? And then what's the situation over here? Let's see. So all of these numbers should give me 0. So I have +2 over here. I don't know what is for the sulfur atom. Let's say it's X, and then I have -6. They all should give me 0. Okay, let me make a little bit of space over here for our next calculations. I hope it is making sense so far. So let's do I have +2 and have -6. It would give me -4 and then +2x. It should correspond to 0, and then 2x should be equal to 4, then x should be equal to 2. So that means one sulfur atom should correspond to +2 oxidation number. Make sense? So 2 sulfur atoms should correspond to +4. So you see over here, you can cross check your answer. +2 +4, it's +6, and this is -6, right? They should add up to give you 0 as the answer. Okay, so I hope that's clear. We have done 3 different types of problems, how to solve for oxidation numbers, and then there's practice problems. Go ahead and give it a try. solve them on your notebook and then we can discuss them. Okay.